Okay, we're ready for implicit differentiation, and this is going to lead us right into related rates, which is one of the harder sections in derivatives. All right, so what is implicit differentiation? Well, generally speaking, the way you're going to notice it is because the instructions are going to have the words implicit differentiation in them, okay? So that's half the battle. Other times they won't mention it though. And by the way, when we say implicit differentiation, differentiation is what we've been doing throughout this section of calculus, taking derivatives of things. To differentiate is to take the derivative. So that's just what we're talking about. We're looking for the derivative. The way you're going to spot these problems, if they don't use the word implicit in the instructions, the way you're going to spot them is that they've got y's intermixed in weird ways. Like normally don't they give you y equals some stuff, but here we've got y in the middle of this problem. We've got a dy dx. Now what is dy dx? It is the derivative of y with respect to x, but really it's just y prime. All right, so let's get into this and see what we got to do. The big trick, by the way, is always going to be to put a y prime or a dy dx next to things. All right, so implicit means in the middle. So that's what I was saying a second ago. When you've got y sort of intermingled throughout the problem and you want to take the derivative, when they say take the derivative, they're asking you to find what y prime is. But the problem is that when you take the derivative of an equation like this, you're going to have a couple of different y primes. This term will create a y prime, and this one will create a y prime. And of course, when you find the answer of what y prime is, it can't have a y prime in it. You got to have all the y primes on one side. It's like solving for x. When you solve for x, you can't have any x's in your answer, right? Same thing here. We got a y and a y, two different spots, so we're definitely going to have to use implicit differentiation. What we've been doing in the past is just called explicit differentiation, or just, hardly even needs a name. You always had f of x, which is the same thing as y, equals a bunch of x's, right? So when you took the derivative, we often write down y prime on the left, or we write down f prime, or you might even see me write that dy dx equals whatever. But the point is we took the derivative of the left side, which is just y, and got one of these three things. And then we took the derivative of the right with respect to x, and we just did derivatives the way we always do them. What's crazy is when you take the derivative of something with y's in it, you can't just use the usual power rule. So for example, in this one we're going to take the derivative of y squared. The derivative of y squared is a power rule just like always. It's going to be 2y. But then next to that we're going to have to write y prime or dy dx. And different teachers do it different ways, but these are the same thing. Y prime and dy dx are the same thing. But as you'll see in this problem and all the ones we do in this section, we always have to remember whenever you take the derivative of a y term, any y term, it's got to have a y prime or dy dx next to it. And that's the way to get these wrong if you're trying to do that. Not really, right? But the thing you really want to be careful of when you first see one of these problems, and if you're good at these and have practiced a lot, then right when you walk up, you're going to say to yourself, oh, how many y's do I see in the problem? So like in this one, I just see a single y term. So I know there's going to be a single y prime that I'll have to like solve for. If there had been two y terms, I'd have to I'd know I'd have a little bit harder situation, and we'll get to those in a second. All right, so the question is find dy dx or y prime from this equation. So first thing to always do is just take the derivative of the function. So any x terms are just going to do the usual thing. The derivative of 2x is just 2. But y terms, like I said a second ago, we've got to write 2y, which is just the derivative of y squared, but then we have to write times y prime. And that is the thing that's easy to forget. And then, of course, the derivative of 3, still 0, just like always. So we're just taking the derivative of everything on both sides of the equal sign. All right, so that's step number one. Just take the derivative of everything you see and be really careful to remember you got to put a y prime next to every single y term that you took the derivative of. At this point, the problem was, they asked us to find y prime, and there's a y prime, so all we have to do is solve for it. So we're going to subtract 2 from both sides. So we'll get 2y, y prime equals negative 2. Then I want to get y prime by itself, so I'll just divide by 2y to get it by itself. That'll cancel that, and we'll get y prime equals, and these 2's cancel, sorry. So we'll get negative 1 over y. Oops, that's y prime. So dy dx, or y prime, equals negative 1 over y. Now you'll notice this is kind of wacky. All the derivatives we've ever taken before only had x's in them. Or, theta or whatever the variable was. but they never have both x's and y's in the derivatives. But that's going to happen. The derivative of y actually has a y in it, and that's totally wacky. So usually what's causing that is that these aren't actually functions. So if you graph this thing, it would be hard. You can't just type it in your calculator. But if you actually graph this thing, you'll find it is not a function. This particular thing is actually a sideways facing parabola, but it's both halves. It's not just the top like you'd normally have a, normally a square root function is just a something like this. But x equals y squared is actually both halves of that parabola. It's a full sideways facing parabola. All right, getting ahead of myself a little bit. I'm just telling you how to graph these things, but the point is these are not functions, and that's why the derivative will often have a y in it. All right, so once again, find y prime or dy dx given a formula. So let's take a look. Now this one's a little bit tricky, and I'll show you why. It's only because, like I said, the only mistake you can make in these, this mistake you're going to make almost all the time you make a mistake, is forgetting that y prime. So the derivative of x squared is 2x. Derivative of y is 1, isn't it? And the derivative of 2x is 2. Oh wait, how am I going to solve for y prime? I don't have a y prime in this equation. Where'd it go? Well, I forgot something, didn't I? I forgot the derivative of y, sure it's 1, but I always have to, anytime I take the derivative of a y term, there's always a y prime. Even if there's no y's left, there's still going to be a y prime. And obviously this one was easy to spot because without any y primes I'd be like, well, what do I solve for? Anyway, but now that we remembered we have this y prime term, now it's easy to solve. Just subtract 2x from both sides. And now we get that y prime equals 2 minus 2x. Alright, so it turned out to be not that bad, but as I showed you, it's really easy, especially when it's just y to the first power. It's so easy to forget that that thing needs a prime. Alright, what if y appears twice? What's going to happen? Well, it turns out we're going to have one y prime for every single y we have in the original problem. So just looking at this problem right off the bat, and I would encourage you to think this way too when you see stuff on tests and things, just take an inventory right when you sit down, right when you open up to a problem, say, hey, there's 2 y's in this problem, so I'm going to have 2 y primes. And as you'll see, that's going to add an extra step to the process, but it's still fundamentally the same. So, anticipating, we're going to have 2 y primes in this problem. All right, let's take a crack at taking the derivative. X squared is just 2x, as we've been doing. Now 2xy, this is actually a product, so I need to figure out some stuff, because this is a product rule, since we have 2x times y. So I'm just going to go over here real quick and work that separately. If I have 2xy, so I'll just call this my u, and call this v, for the purposes of my product rule. So that means, so u is 2x. Sorry, u prime is the next one we want to do. It's just going to be 2. V is y. Now v prime, got to be careful, is y prime. And that's where the implicit thing bites us in the butt, right? So now I've got my u's and v primes and everything. I can just come back and fill it in right here. So the product rule in this puppy is going to be u, which is 2x, times v prime, which is y prime, plus v, which is y, times u prime, which is just 2. And then that gets added to the derivative of y squared, which is just 2y times y prime. So there's my second y prime I was anticipating. And derivative of 9, that's a constant, so the derivative is 0. All right. So just take an inventory. You'll notice I have 2 y primes. It's going to be tough to solve for y prime without the trick I'm about to show you. So what we're going to do is we're going to factor out a y prime, and then which means we need to put everything that doesn't have a y prime in it on the other side of the equation. So I'm going to take away a 2x from both sides, and I'm going to take away a 2y, so that I'll just have the y prime stuff on the left. So now I got 2x y prime plus 2y y prime equals negative 2x minus 2y. Now at this point, you see how everything on the left side of this equation has a y prime in it. So I can factor out a y prime plus 2y. And that was really important. If I hadn't done that, if I tried to solve for this y prime, I would have had a y prime on the right side. If I tried to solve for this one, it would have been a y prime. The only way to take two terms that both have the thing you're solving for in them and get it down to solve them just once is you got to factor it out. So that's what we've done, negative 2x, negative 2y. Now here's what's awesome is once you factor it out, all we have to do is just divide by whatever's in the parentheses. So 2x plus 2y will cancel all that junk. And of course I have to do the same thing to the other side. So at this point I've got y prime, and that's the whole point of the problem, is trying to find out what y prime is. It's kind of this messy fraction. Now you could walk away at this point, but if I was you, I'd start factoring stuff out. So y prime equals, now we can factor out a -2 from upstairs. And we can factor out a 2 from downstairs. Oh, look at that. X plus y is cancel, and that's okay. That's legit. So it turns out y prime just equals -1. So out of all these derivatives and junk, we just get y prime equals -1. Pretty crazy. Honestly, I did not plan that. I just kind of whipped up this problem, but very cool that that worked out that way. All right, so the moral of the story was, whenever you sit down on one of these problems, count up the y's. In this case, we had 2 different terms that had a y in them, which means we're going to have 2 y primes to work with as we solve the problem, which means we're going to have to do this trick right here, which was factoring the y prime out of the stuff on the left. So we'll get some chance to practice that again right now, because check this out. We have another problem that's got a y term right here and a y term right here, which means we're going to have to factor out the y prime again. Now this one has the chain rule. That last one had the product rule, because we had that 2xy term that had to use the product rule. This one we've got the chain rule a couple of times. So I'll show you where. Shouldn't be too surprising since you guys are all chain rule experts by now. But so we got plus 2 sine y. That doesn't necessarily look like a chain rule, but it is. Because remember, cosine x or sine of x is the only thing you can take the derivative of without the chain rule. Because it's a y instead of x, that means we're going to have a y prime term, right? Because every y term in the original is going to generate a y prime. And where that comes from is from the chain rule. The derivative of sine y is going to be cosine y times u prime, or the derivative of whatever the sine is of. And that, of course, is y prime. And for this one, same deal, the chain rule again. Do a power rule, y plus 3 squared. But then we got to multiply by the derivative of what's inside the exponent. And that is y plus 3, derivative of y plus 3, y prime. So that's, and of course, derivative of 9 is still 0. So that's where you got to be careful. We just took the derivative of y once here, and both times we got a y prime. They can be a little bit tough to spot, but that's why it's so important. If you just count up the number of y's you had originally, you knew you were looking for 2 y primes in this step of the process. And that's just a really great way to double check yourself, because the number one mistake students make in this type of problem, or just implicit differentiation problems, is that you just forget one of the y primes. It's like you're going through all these derivatives, you leave off one of the y primes, and then you're hosed. And as you'll see in related rates problems, same thing's going to happen. In related rates problems, we'll be taking the derivative with respect to t instead of x. But whatever, the point is that every time you take the derivative of a letter in related rates, you're going to have that v prime or t prime or whatever next to it. So that's just implicit differentiation, same thing. Every time you have a y in the original, you're going to have a y prime in the next step. All right, so at this point, we're just going to do the usual deal. We need to get everything with a y prime on the left and everything with not a y prime on the right. And the only thing here is a 2x. So I'm just going to subtract 2x. And we'll just make that, negative 2x over here. Save some writing. All right, so let's factor out a y prime. So we'll get 2 cosine of y plus 3 times y plus 2 squared. All right, equals negative 2x. So now I just got to divide by all this junk. And that'll leave me with y prime. That equals negative 2x over 2 cosine of y plus 3 times y plus 2 squared. Pretty crazy. But remember, I keep drilling this in. If there's 2 y's in the original problem, 2 y primes, got to factor it out at this step, and then just divide by whatever's in parentheses. All right, so this is yet another problem, exactly the same. This is the last one we'll work in this particular video. So if you're getting the hang of this, you can move on. Why did I say recognize this one, question mark? It's because this is actually the equation of a circle, which is kind of cool. But if you just rearrange this using algebra, squared both sides, combine terms, you get x squared plus y squared equals 9, which is a circle of radius 3. So that's just kind of a fun factoid. All right, so here we are. We're just plugging and chugging, solving for y prime as usual, even though I didn't state that in the instructions. what you're doing with implicit differentiation is always just solving for y prime. So let's take a crack at it. First thing I want to do is rewrite this as a power, because whenever you're taking the derivative of a root, it's just way easier to think of that as a power rule situation. So rewrite it as 9 minus y squared to the 1/2 power. Now I can just do power rule. But of course it's power chain rule, right? So 1/2 out front. Then I got the same stuff. New exponent. Now I got to multiply by u prime, and since my u was all this stuff under here, that means my u prime is negative 2y, just the derivative of negative y squared, times y prime. And the derivative of the right side, which is x, is just 1. Alright, so first things first. Oh yeah, so I can cancel this, negative 2, and the 1/2. Just give us a negative 1. You know what, I'm just going to move that out front so I don't forget it. So negative 1 out front. And now I want to isolate y prime, right? Luckily in this problem there's only one y in the original, so there's only one y prime. So all I have to do is just divide by all this stuff. So divide by negative y times 9 minus y squared to negative 1/2. Alright, so y prime equals negative 1 over y times 9 minus y squared, negative 1/2. But, negative 1/2 downstairs is actually the same thing as positive 1/2 upstairs. So I'm just going to have negative 9 minus y squared to the 1/2 over whatever's left, which is just y. Oh my gosh. Oops, this is y prime. Alright, so that is implicit differentiation in a nutshell. In case you haven't noticed, the big mistake you do not want to make is forgetting those y primes. So definitely practice these. Maybe do the same problems I just did. Work them out for yourself. If you're doing your homework problems, check the answers in the back of the book to make sure you're getting them right. Because the easy thing to do is forget that y prime, or forget one of them, and then you get the wrong answer because, obviously the algebra changes if you have one less y prime than you were supposed to have. Alright, so stick around. We're going to start applying this next. It's going to be fun.